Hello everyone. So in this video, I'll talk about a question on how to graph a rational function by using our basic features of the rational function. So most basic function that we know in terms of rational function is 1 over y equals 1 over x. Okay, so this is the parent function of the rational one, and we want to kind of use this as a guide to get a bit complicated version of these. So what we want is the graph of 2x plus 3 over x plus 1. So since we are asked to use the long division, I'll go with that first. So 2x plus 3 divided by x plus 1. So, we want to ask how many x should go to the 2x, which is 2 times x, right? So we just start with 2. 2 times x is 2x, and then 2 times 1 is 2. And when we subtract, so these will cancel. 3 minus 2 is just 1. So that is my quotient. This is my remainder. So meaning that this g of x can be written as 2 plus 1 is my remainder. So we were just writing 1 over x plus 1. This is what we used to do when we talk about the long division. But to be honest, I wouldn't use this one, especially for this simple question. So because the reason why I like something doing else instead of doing the long division, because the numerator and denominator are not too complicated. So if you look at the numerator, I can easily see if I multiply this x plus 1 by 2, I will get something in numerator. So let's actually write that as well. So I can say 2 times x plus 2 plus 1. I just split 2x plus 2 because that is twice as much of the denominator. So I can split that as a different denominator. So x plus 1 divided by x plus 1. And this is 2 times x plus 1. That is x plus 1. So if you divide 2x plus 2 divided by x plus 1, you can pull 2. When you pull 2 as a factor, so you will get x plus 1 times 2. So x plus 1 will cancel. So you will get 2 plus 1 over x plus 1. And that is exactly what we have. And then just a reminder, one of the most like general way that we usually write to rational function was this way. So I'm going to say g of x equals a times 1 over x minus h plus k. And then the a is vertical like stretch or vertical dilation, I would say, and k is the vertical shift, and then the h is the horizontal shape. So the a, k, and h are our basically key like values that we are going to use to graph our function. And now we call those a, k, and h the parameter of the function. Okay, so that is just another term that we use to represent all these key like variable. Okay, a, k, and h. So why this is important? Because we are going to kind of use these and see how this is going to be affecting our graph. So our graph is this, like 2 plus 1 over x plus 1. So I'm going to rewrite this a bit differently. So g of x is equal to, instead of writing 2 first, I'm going to write after. So this could be written as 1 over x. Instead of x plus 1, you may write x minus minus 1 and then plus 2, because I like to get my h value, which is just -1, and then my k is 2. So by using this, I'm going to find the relation and how this is going to affect my graph. And then there is no a, which means that is just 1 times this fraction, basically, which is easier in this case. So the couple things we have to find is the vertical asymptote. So I'm going to take a vertical asymptote first. So the vertical asymptote, you know, when you shift this graph by 2 units right here, that will be moving the graph 2 units up. So if you kind of remember the general version of the 1 over x, maybe I should remind it as well. So graph of this, I'm gonna use it right here, just to make it a bit reminder. So graph of this was something like this, right? So it was this forever, and then we do have this. So this is the graph of y equals 1 over x, okay? But now, if you are shifting this 2 units up, so this was my horizontal asymptote, and then this was my vertical asymptote. So if you're like moving this function like -1, which is like to the left, so your graph, this graph will shift into the left by 1 unit, and then you can see the denominator x plus 1. So whenever you have like add something to the x, that is the amount you are going to shift into the left. So this graph will be shifting to the left by 1 unit. So that means the vertical asymptote, which is x equals 0, is going to move to the left by 1 unit. So which is why the vertical asymptote is equal to x equals -1. And similarly, horizontal asymptote, right? So it was y equals 0, but now you are shifting 2 units up. So if you shift this graph 2 units up, so you will get y equals 2. So that is my horizontal asymptote. And we have 2 reference points. So I'm going to say reference points. One of them is 1, 1, right? So we want to see what this is like, these values will be when I actually get this graph. So the x value is 1, but when you look at the graph, x value will be shifted by h unit, but this a doesn't affect the x value. This a affects our y value, this k affects y value. Only thing is going to affect the x is h, but if there is some like coefficient of x, that would be, but in this case we don't, so we are good with that. So if you are like moving your graph 1 unit to the left, the x value 1 is going to decrease by 1, so you will get 0, okay? And now y value, since we are going to multiply by a, but in our case, there is no number right here, so which is 1, so it doesn't really change my 1, but our k is going to be vertical shift, so it is 2, so we are going to increase 1 by 2, which will be 3, okay? So that is your first reference point. And the second reference point is -1, -1 that we use. So the x value is kind of acting the same as this one. So it was moving to the left by. So if you decrease by 1, so you do get -2. And then the y value will be increased by 2 in our case because it's shifted 2 units up. So if you increase -1 by 2, you will get +1. So now we have those reference points. So let's go ahead and graph our function, and then we will find the range and domain as well. So first things we want to graph is vertical asymptote or the horizontal asymptote. So the vertical asymptote is x equals -1. So this is -2, so the -1 should be like something right there. So I'm going to draw this. It's not really right in the middle. So let me try this a bit better. So if you draw this x equals -1, that's your vertical asymptote. And then the horizontal asymptote is going to be y equals 2. So 2 is right here. So it will be this line. So the y equals 2 is your horizontal asymptote. And the reference point is 1, 1 will be moved to 0, 3. So 0 is right here. So 3 is right in the middle. So that should be somewhere right there. And the next, the reference point is -1, -1 is just moved to -2, 1. So that is -2. And this is -2, this is -1. So that looks like this point. So again, we are going to expect something like this, but now this like reference point was 1, 1, and -1, -1 is going to be this one and this one, and horizontal and vertical asymptote, it just like change a bit. So you are going to approach this line, but not touch, and then you are going to pass through this point. So the graph will look like this. Okay, so you are going to continue this forever and then continue this as well, but you are not going to touch y equals 2. You will just getting too close, but that would be your horizontal asymptote. And the same idea on this part. So if you were to draw, so you will see something like this. Okay, so that is the graph of this function. So if I want to find the last thing as my domain, so let's do that as well. So for the domain is anything except the number that is on my vertical asymptote. So the vertical asymptote is -1. So domain is anything but -1. So which is like we can just use this notation. X could be anything. X is such that X is anything but -1. And then that is the domain. And then the range is anything but this horizontal asymptote, which is 2. So you can say y would be anything but y equals 2. Okay, so that is my range. So I hope this is clear. So we just use the basic features of the rational parent function y equals 1 over x and just transform that into our new function. And then we got the graph and some of the other features as well. So I'm gonna leave for you to think about the end behavior of this function. So, but I will say it is good to think about as well. So this is it for now. I'll see you in the next one.